We now move to the problem of radioactivity, that means radioactive decay. So this is also known as radioactive decay. And scientists stated a very simple law of decay that they found experimentally, which states that the rate of decay is proportional to of a radioactive mass is proportional to the mass remaining. In other words, if there is a certain mass of a radioactive material that is decaying naturally, and if its mass is m at any point of time, in other words, m is m as a function of t, then what the law says is that dm dt is just proportional to m. In other words, this implies that dm dt is nothing but k into m. It's a very simple law, and it is a good example of how to model information that we gather from the world of physics into a mathematical form, so that we can see how the mass remaining at any instant of time is a function of time, with, of course, t is equal to 0 being the point from which we start observing or looking at a particular mass which has a particular weight or mass. So we will start by restating the problem that if there is a radioactive mass and m at 0 is considered as m0, m0, this is the initial mass. This is m for t is equal to 0. T is equal to 0, it can be any point of time. Sometimes students have a little bit of difficulty with trying to understand what is negative time. So they say that how can time be negative? Well, let us say that 12 o'clock is t is equal to 0, then 11:55 in minutes will be t is equal to minus 5, and 12:05 will be t is equal to plus 5 if we measure the time in minutes. So this is the initial mass, and this is an initial condition actually. We can write this as an initial condition. Now the question is, there is a little bit of extra things we have to say about k. Because it is decay, this k has to be negative. So it is better to write this as in a different way. dm dt is, say, minus k1 into m. And then this k1 is certainly positive. If we write it as plus k, just km, this is negative. So we have captured that situation in writing minus k1 m with the stipulation that here k1 is greater than 0. That ensures that, my friend, minus k1 is negative. So we will solve this. This actually does not take much time to solve. We will remove all this. This can be written as dm over m is equal to minus k1 dt. In the next step, we can integrate both sides. So This implies the integration dm over m is integration minus k1 dt. The next line will easily be log of m to the base e is minus k1 into t plus c. Now this is the solution of the very simple differential equation that we had written. We just have one task left, and that is to find the value of c from the initial conditions. We just rubbed out what we had written, that when t is equal to 0, the value of m is m naught. So putting those values, we get log base e m naught is equal to t is equal to 0, so this term will vanish, so that is c. So this equation reduces to log e m is minus k1 t plus c, which is log e m naught. We can do one thing. We can take this log term this side and carry out the simplification a little up on the board. From here one can write log em minus log em naught is minus kt, or log e m by m naught is minus kt, or m over m naught is e to the power of minus kt, and this finally implies that m is m naught e to the power of minus k t. This k is a constant which is different for different types of materials. Now let us see a further analysis of this. While on this subject, it's not that we are just solving a differential equation or modeling it. We have to just get a little further and to answer a very simple question which arises in radioactivity, and that is, how long does it take for the mass at any instant of time to become half of the initial mass? And that time is called the half-life for that particular material. We'll answer that question by writing what is the half-life of any particular substance. Half-life means time taken for any radioactive mass to become half its initial mass. Half of its initial mass. That's a very simple job mathematically. Actually, we just have to replace this m by m naught over 2. So, if we write that let the corresponding time be capital T, okay, when m becomes m0 by 2, then we can write m0 by 2 is m naught e to the power of minus k t, where actually I can write better t sub half. where t sub half tells us the time at which the initial mass of m naught becomes half its initial value. Now, getting rid of this m0, we get e to the power of kt half will be 2. That means taking reciprocals of both sides, we can get 2 is equal to e to the power of kt half. So, if you want to get the value of t half, we just do the following: take logarithms to the base e on both sides, and we will just have a very simple equation. Log base E2 is k t half. So, t half for any substance is log E2 divided by k. This is log to the base E2 divided by k. That is the half-life. One important thing about half-life is that supposing we take two half-lives. In the first half-life, m0 becomes m0 by 2. In the second half-life, m0 by 2 will become m0 by 4. So, if we have a very simple problem, if, for example, we take 640 grams, 640 grams of any material, after one half-life it will become 320. After two half-lives, it will become half of this, 160. After three half-lives, it will become 80, and so on. One can see that after 6 half-lives, it will get to 1 by 2 to the power of 6 of 640, and that is nothing but 10 grams. Now, half-lives can be in years. If I can recall correctly, one isotope of carbon, which is radioactive, has a half-life of around 5,700 years. So, it's quite a long time. And that is how carbon dating is used to find the age of fossils. So, that's all for now. Before leaving this topic of radioactive decay, we can see or try to see another parallel situation in which instead of saying decay, we will have growth. And that applies to bacterial cultures. Certain cultures, they grow at a rate such that the rate of growth of the bacteria in a conducive medium, of course, is proportional to the number of bacteria present at any instant of time. In other words, the dm dt is proportional to m, which is the same equation which we wrote for the decay, and then we said that this would imply this is equal to Km, putting K as a proportionality constant. But here, because it is growth, we can write this is the growth, sorry, there should be a W, growth of bacterial cultures. Here, because it is a growth and dm dt has to be positive, otherwise it would imply negative, this K is essentially greater than 0. And evidently one can see that the equation is dm is K m dt. In other words, dm over m is k dt. When we integrate this, we can write an integral sign on both sides. This is k dt So the integral becomes kT plus C. Here we get, as before, log EM is kT plus C. In other words, m is equal to e to the power of kT plus C. So this implies m is equal to e to the power of kT plus C, which can be written as e to the power of kT into e to the power of C. And this e to the power of C can be replaced by a simple constant as, say, A. So m is equal to A into e to the power of kT. So this is the solution. Now what exactly is this m, or this A rather, in terms of m? That should be very simple to answer, because if we put t as 0, e to the power of kT is 1, and A becomes m naught. So this A is nothing but m naught. We will do it a little above so that there is a simpler understanding. If m is equal to A e to the power of kT, we put t is equal to 0, m is equal to m naught. This is the initial number of bacteria. So A has no other value than m naught. So one can write m is equal to m naught e to the power of kT. Now instead of half-life, we can do one thing. We can ask ourselves, how much time will it take for this mass or this mass actually to get to 2 times of the initial mass, means number actually. So when T is T2, this is the time taken for the culture to double, m becomes 2m naught. We write down 2m naught is equal to m naught e to the power of k t double time. If we knock off this, we get k t2 is log of 2. K t2 is log base e2. In other words, t2 is nothing but as we said before, for radioactive materials, the K is reflective of what bacteria we are talking about, and these can be experimentally found. So this is the double time, very similar to the half-life of radioactive decay.